Everyone, welcome back. So, implicit differentiation seems rather confusing at first, but I always like to remind my students that it's really not that much different than the derivation that you've already been doing up until this point. The key difference is the starting equation. So, up until this point, you've been taking the derivative of equations that already have y isolated. So, an example of that would be y equals x squared, right? So, then we would rewrite this as y prime equals 2x. We could also write y prime as dy dx. And this is where you're really going to see the similarities. So with implicit differentiation, the key difference is that we don't have y isolated. Our starting equation is going to be in terms of both x and y. So a very simple example of that could be a circle. So it could be x squared plus y squared equals 25, right? And then when we take the derivative of this, the key thing to remember is that when we take the derivative of our y term, we have to write dy dx after it. You can also use y prime, but I don't recommend that because I find that my students just find it harder to distinguish between y prime and y rather than dy dx. Okay, so with that out of the way, let's go ahead and continue on with the lesson and go over some key applications of this. So we kind of already talked about the first one, which is just finding slopes and tangent lines of certain curves that can't be written explicitly in terms of y, or it could just be very difficult to write them explicitly in terms of y. So for example, like sine of xy or e to the xy. These are cases where we're definitely going to want to use implicit differentiation. And basically the idea is that after we've taken the derivative, again, we're going to have our dy dx in the midst of our equation. So then we have to use algebra after to isolate dy dx. Whereas if we're starting with an equation that's already solved for y, right? So again, going back to this example, then when we take the derivative, we immediately already know what our dy dx is, right? Without having to do algebra. But if we don't do that, if we use implicit differentiation, then oftentimes we have to take the derivative, then do algebra to isolate dy dx. Okay, anyway, so continuing on, second key application is kind of related to the first one. It's just analyzing curve behavior. So after we use implicit differentiation, oftentimes we will then want to analyze it and we will want to see where our horizontal or vertical tangents are. Another important application is related rates. So these happen when we have two or more quantities that are changing together over time. So for example, actually we can just use this example. So x squared plus y squared equals r squared. We could use implicit differentiation to take the derivative of this with respect to t. So another key application is the second derivative. So if we just take the derivative again, we can use that to analyze concavity and find points of inflection. And then the last one is differentiating inverse functions, which we're not going to go into in depth on this video because there will be another video on this. But just know that it is a technique used to differentiate our inverse trig functions, for example. Okay, let's go ahead and move on to some problems. Okay, so let's take a look at number one. Just as a quick refresher, this is the equation of a circle with a radius of 5 that is centered at the origin. We can immediately notice that this is a good candidate for implicit differentiation because we have x and y on the same side, right? We do not have y isolated. So let's go ahead and take the derivative. Okay, so first, the derivative of x squared is just 2x. And then the derivative of y squared is just 2y. However, we have to remember to write dy dx after it. And then we are going to take the derivative of the constant 25, which is just 0. So now we have to actually perform the algebra. So that means now we're going to work to isolate our dy dx term. So let's go ahead and subtract 2x from both sides, which would give us 2y dy dx equals negative 2x. And now we're just going to divide by 2y on both sides. And then we're just going to simplify our right side there by canceling out the 2's. And then we're going to get dy dx equals negative x over y. Okay, let's go ahead and move on. Okay, so for number 2, it says if x cubed plus y cubed equals 9xy, then at the point 9 over 2 comma 9 over 2 dy dx equals what? So again, great candidate for implicit differentiation because we have our x and y together. We do not have y isolated. So let's go ahead and take the derivative. So the derivative of x cubed is just 3x squared. The derivative of y cubed is 3y squared dy dx. And that's going to be equal to the derivative of 9xy. Here we are going to use the product rule. Personally, I like to just group basically my constant in with my first term. So I like to group 9x and then I consider my second term to be y. That's personal preference. If you prefer, you can also just pull the constant out front, meaning you can basically like factor it out like 9, and then you can just do the product rule for x, y. However, like I said, I'm going to consider my first term to be 9x and my second term to be y. Okay, so now using the product rule, we do the first, which is 9x, times the derivative of the second. So the derivative of y is just 1 dy dx, and then plus the second, which is y, times the derivative of the first, which is just 9. Okay, so now we're going to clean everything up, and then we're going to use algebra to isolate dy dx. So this side is pretty much going to stay the same, so I'm just going to rewrite it. And then over here, this is just 9x dy dx plus 9y. Okay, now we are going to move our dy dx's to the same side. So I'm just going to move this one over to the left side by subtracting, and I'm going to move this over to the right side by subtracting. So I'm going to get 3y squared dy dx minus 9x dy dx is equal to 9y minus 3x squared. All right, now I'm going to go ahead and factor out my GCF of dy dx on the left-hand side. So that would give me dy dx times the quantity 3y squared minus 9x is equal to 9y minus 3x squared. All right, now I'm going to go ahead and divide by this on both sides. 3y squared minus 9x. It's going to cancel out. And now I have my dy dx equation. So let me just clear the screen and then we'll continue on. Okay, so what we have here, I just cleaned up the screen and just rewrote dy dx. The next thing we can do is we can actually simplify everything down by a factor of 3. So our fully simplified version of dy dx would be 3y minus x squared over y squared minus 3x. Okay, so now we have our derivative, which again just represents the slope. So now we are going to use our point. So we have 9 over 2 comma 9 over 2. And we are going to plug that in for both x and y. So let's go ahead and do this. This will become 3 times 9 over 2 minus 9 over 2 squared over 9 over 2 squared minus 3 times 9 over 2. You may already notice here, just from looking at it, that we are going to end up getting -1, because notice we have the same exact values just being subtracted from each other in a different order. But let's go ahead and just prove that to you in case it's not that obvious. All right, so here we just have two fractions that are being multiplied, so we just multiply straight across. So this would give us 27 over 2 minus 81 over 4, and then all over 81 over 4 minus 27 over 2. Again, you might be able to see that more clearly now, how it's going to be -1, but let's keep going. I'm going to move up here. All right, and then once we get a common denominator, this is going to become 54 over 4 minus 81 over 4, all over 81 over 4 minus 54 over 4, which is going to give us -27 over 4, all over 27 over 4, which is just equal to -1, which would be answer choice C. Okay, so for number 3, we are going to have to use the chain rule. We have e to the power of x times y equals x plus y. So let's go ahead and take the derivative of the left side first using u substitution. So I'm going to let u equal x times y, and then I'm just going to rewrite e in terms of u and take the derivative. So actually, let's go ahead and do u prime now. So here we're going to have to use the product rule. So we're going to do the first times the derivative of the second plus the second times the derivative of the first, which is just 1, so I'm just not going to write that. All right, and now we're going to rewrite the derivative of e in terms of u. So it's going to be e to the u because the derivative is itself. And then using the chain rule, we're going to multiply that by u prime. And then let's go ahead and actually take the derivative of the right side. I'm being slightly sloppy with my notation just because I don't have a lot of space. So we're going to take the derivative of the right-hand side just regularly in terms of x. Again, please excuse my sloppy notation here. All right, so the derivative of x is just 1, and then the derivative of y is just dy dx. All right, now let's go ahead and plug back into the left side for u. So we're going to have e to the xy times x dy dx plus y equals 1 plus dy dx. Okay, now we are going to have to do algebra because we have to isolate dy dx. So first things first, let's go ahead and distribute that in. So we're going to get e to the power of xy times x dy dx plus e to the xy times y equals 1 plus dy dx. All right, now I'm going to move all of my dy dx terms to the left, and I'm going to move everything else to the right. So basically, I'm going to subtract this over to this side, and I'm going to subtract this over to this side. Apologies again, just because I'm running out of space. So hopefully that all makes sense. Okay, so moving up here, what we're going to have on the left-hand side is this e to the xy times x dy dx term is just staying where it is. Then I'm going to subtract dy dx. And then that's going to be equal to, my 1 is just staying there. And then I'm subtracting e to the xy times y. Please feel free to pause the video and do that on paper using actual proper notation if needed. Okay, now on the left-hand side here, I'm going to go ahead and factor out dy dx. So that will leave me with dy dx times e to the xy times x minus 1 equals 1 minus e to the xy times y. Okay, and now I'm going to draw just a little barrier here. And now I'm going to use division. So I'm going to divide by e to the xy times x minus 1 on both sides, x minus 1. And then I'm going to be left with dy dx is equal to 1 minus e to the xy times y over e to the xy times x minus 1. All right, let's go ahead and take a look at our answer choices. And this looks like it is answer choice B. All right, let's go ahead and move on. Okay, so for this one, we have sine of xy equals y. So we are going to have to use the chain rule here. So let's go ahead and let u equal x times y, and then let's find u prime using the product rule here. So it would be the first times the derivative of the second plus the second times the derivative of the first, which is just 1, which is why I'm not going to write it there. So then if we rewrote the left-hand side in terms of u, we would get sine of u. And then if we took the derivative of that using the chain rule, we would get cosine of u times u prime. So let's go ahead and plug back in. That would give us cosine of xy times x dy dx plus y. Now let's go ahead and take the derivative of the right-hand side, and the derivative of y is just 1 dy dx. All right, now let's go ahead and use algebra. So we're going to go ahead and distribute this in to start. So that would give us x cosine of xy dy dx plus y cosine of xy equals dy dx. Okay, now I'm going to subtract this term over here to the left, and I'm going to subtract this term over here to the right. So then I would get x cosine of xy dy dx minus dy dx equals negative y cosine of xy. Okay, now I am going to factor out the GCF on the left-hand side, which is dy dx. So I would get dy dx times x cosine of xy minus 1 equals negative y cosine of xy. Okay, now I'm going to divide by this on both sides. So that would give me, let's see, actually, let me just write out my work so you can follow along. X cosine of xy minus 1. Okay, and so now this would give me dy dx equals negative y cosine of xy over x cosine of xy minus 1. Whew. Okay, now let's go ahead and take a look at our answer choices. So it looks like they just did not include this negative sign here. So if we took all of this and multiplied through by negative 1, we would get dy dx equals y cosine of xy over 1 minus x cosine of xy. So that's basically me just multiplying through everything on top and bottom by negative 1. And that would give us answer choice C. Okay, so now let's take a look at number 5. This question says x squared plus xy plus y squared equals 7. And we are looking for the slope at the point 1, comma 2. So again, we have to know that the slope basically is represented by dy dx, and we're going to have to use implicit differentiation here. Let's go ahead and jump right in. So the derivative of x squared is 2x. Now here for xy, we are going to have to use the product rule. So first times the derivative of the second plus the second times the derivative of the first, which again is just 1, so I'm not going to write that, and then plus 2y dy dx, and the derivative of our constant 7 is just 0. Okay, now let's basically move everything that does not have a dy dx attached to it over here to the right-hand side just by subtracting those terms over. So these two terms are going to stay. The other two are going to get subtracted. So minus 2x and minus y, and over here, minus 2x and minus y, basically like that. Okay, so on the left side, we still have x dy dx plus 2y dy dx equals negative 2x minus y. Now we are going to factor out our dy dx, and I hope at this point you're kind of seeing the repetitive nature of the algebra here. So basically you're getting your dy dx terms to the left-hand side, then you're taking out the GCF, then you're basically dividing on both sides to isolate dy dx. Anyways, okay, so continuing on, over here, we would have x plus 2y, and this equals negative 2x minus y. Now we're going to divide by x plus 2y on both sides, x plus 2y. So now we have the equation for our slope, which is just dy dx equals negative 2x minus y over x plus 2y. All right, and now we are going to plug in for our point, which is 1, comma 2. So I'm going to move back up here. All right, so negative 2 times 1 minus 2 over 1 plus 2 times 2. So again, I just plugged in 1 for x and 2 for y. Now let's go ahead and just simplify here. This would give me negative 2 minus 2 is just negative 4 in my numerator. And then this is just 1 plus 4, which is 5. So this represents the slope of this equation at this point. And the correct answer would be answer choice A. Okay, so let's go ahead and take a look at an FRQ and see how we can apply implicit differentiation to a related rates problem. Okay, so this tells us a particle moves along the curve x squared plus xy plus y squared equals 7. And just a quick note, we actually just solved this in the last question, so you should be pretty familiar with this at this point. And it says at the instant when x equals 1 and y equals 2, so we have that same point 1, comma 2, and dx dt equals 3, find dy dt. Okay, so how do I know this is related rates? Well, this really, the fact that we're differentiating with respect to t is kind of tipping me off here. All right, so we are going to take the derivative of this again. It's going to be similar to the first time that we did it, but note that this time we are taking the derivative with respect to t. So what that will mean is that now when we take the derivative of x squared, it isn't just going to be 2x, it is now going to be 2x dx dt. All right, now next we have xy. So again, we have to use the product rule. So it's the first times the derivative of the second. But again, now since we're differentiating with respect to t, this is now going to be dy dt. So plus the second times the derivative of the first, which is now going to be dx dt. Okay, and then plus now the derivative of y squared is just 2y dy dt. And then the derivative of our constant 7 is still just 0. So again, note that this is similar but slightly different. Because we are no longer differentiating with respect to x, we are now also having to write dx dt everywhere, right? And really, I mean, even when we were doing this before, we could have written dx dx, but it would have just been 1, right? So that's why you don't see it. Okay, so let's go ahead and continue. Now we are going to group together our dy dt terms. So we're going to group these and these over on the left-hand side, and we're going to move everything else to the right-hand side just by subtracting it over. So on the left-hand side, we're going to get x dy dt plus 2y dy dt. And then again, we're going to subtract both of these terms over. So we're going to get negative 2x dx dt, and then minus y dx dt. Okay, now we are going to factor out our GCF over on the left-hand side of dy dt. So then we would be left with dy dt times x plus 2y equals negative 2x dx dt minus y dx dt. All right, now I'm actually going to factor out my dx dt as well, just because it's going to make it algebraically slightly simpler. So dy dt times x plus 2y equals dx dt times negative 2x minus y. Okay, now we are going to go ahead and divide by this on both sides. So x plus 2y divided by x plus 2y. Okay, and now I just cleaned up the screen a little bit, and I'm going to continue on with blue ink just so that you can follow along. So this is going to cancel out, and then I'm going to get dy dt is equal to dx dt times negative 2x minus y over x plus 2y. Okay, so now this is why we were given that dx dt is equal to 3. So now we can go ahead and plug that in. So we have dy dt is equal to 3 times, and now we're also going to plug in for our point. So we're going to plug in 1 for x and 2 for y. So this would give us negative 2 times 1 minus 2 over 1 plus 2 times 2. And again, this should look familiar from the last question we just did. All right, so this would be equal to 3 times. Now in our numerator here, we have negative 4. In our denominator here, we have 5. So 3 times negative 4 is negative 12, and that would be over 5. Okay, so this tells us that dy dt is equal to negative 12 over 5. All right, thanks so much for watching, and I'll see you in the next one.